1.
The beginning of a perfect flight. Man is launched into space atop an Atlas booster. The capsule re-enters the Earth's atmosphere, survives the fireball phase, and parachutes to a pre-selected landing point. A successful and historic flight, one of man's first excursions into space, a journey that required millions of dollars and millions of man-hours, an accomplishment that signals the beginning of a new era. Major participants in helping make this a perfect flight and in opening the threshold of this new era are the people and facilities of the Arnold Engineering Development Center, a part of Air Force Systems Command. A center. In the wind tunnels and rocket test cells of the center, almost every critical point in a space flight can be simulated, from launch through staging, orbital flight, to re-entry. Severe flight environments can be investigated. To describe the work of the Arnold Center, let's take a rocket research spacecraft, the X-20, and see how the center's facilities are used to solve flight and propulsion problems before they are encountered in actual flight. For example, at launch, heating of the booster's base, the performance of the first stage nozzles can be investigated by firing the engines at the center's high-altitude test cells. The ignition and performance of the upper stage rocket motors, and the precise thrust and efficiency of retro rockets and the verniers, all can be observed and evaluated rapidly and economically before the actual flight is attempted. The X-20's flight controls can be tested to predict their effectiveness in space and during re-entry. Will its structure survive the blazing temperatures and extreme forces of re-entry? Can it be decelerated and controlled by its pilot through the re-entry corridor to the Earth's surface? Problems encountered in rocket engines at launch are investigated in this rocket test facility. Engine tests can be performed in high-altitude test cells with scale models like this small version of a Saturn booster. As a result of tests of this type, Arnold and NASA engineers redesigned the turbine exhaust system, substantially reducing the base heating of this Saturn booster. The value of these tests were proven in the first 2 Saturn flights. Watch what happens when combustible gas, representing the turbine exhaust, is released near the base of this Atlas missile. The gas recirculates between the nozzles and burns, a problem that caused the loss of several early missiles. Next, the upper stage rocket motors are tested to determine their performance at very high altitudes. Rocket motors like this full-scale, solid propellant, third stage of the Minuteman can be mounted on a thrust stand to measure precisely their ignition, total thrust, and any variations in thrust during full duration firings. Hundreds of measurements, pressures, temperatures, vibrations are recorded during test firings conducted much like the actual launches at Cape Canaveral. In this test unit, full-scale liquid propellant rocket engines can be tested in their normal vertical flight position. Other facilities at the center, like this propulsion wind tunnel, the largest supersonic tunnel in the world, simulate critical flight conditions for the X-20 vehicle and its booster. Conditions simulate acceleration to supersonic speeds and a climb to higher and higher altitudes. Behind the rocket, a scoop captures the exhaust and removes it from the closed-circuit, continuous flow tunnel. The next step in a typical test program might require simulating on the ground some of the problems involved in staging when the upper stages are separated from the booster, like this actual separation photographed high above the Earth. Scale models of the two stages are placed in a test cell, separated at various intervals to determine if the separation will be clean or if it will affect the course of the second stage. After staging, it may be necessary to duplicate the conditions of coasting in orbit to determine if a satellite rocket engine will function and can it be shut down and restarted in space. In one test, this graphite nozzle failed violently. Subsequent tests using this titanium nozzle provided the answer. Despite high temperatures causing it to glow as it would in space, it survived the tests, and its nozzle was gimbaled as required for directional control of a spacecraft. Another problem. What happens if a spacecraft collides with a tiny meteorite or some space debris during its orbital flight? The air inside this hyperballistic impact range is conditioned to simulate an altitude of 250,000 feet. Tiny particles are then fired into thick blocks of lucite or heavy metal plates at speeds exceeding 5 miles per second. The high-speed camera records the effect. The small, BB-sized particles produce large craters in the targets. Critical problems of a space vehicle's re-entry into the Earth's atmosphere can be studied in these hotshot tunnels. Near the end of the flight, a space vehicle plunges into the denser atmosphere at speeds of 10 to 12,000 miles an hour. Frictional heat as the craft collides with the molecules of air cause the fireball ride of re-entry. These tests predict the rate of heat transfer to the craft, help determine the structure and materials that must be used to prevent the craft from burning up. A careful analysis of test data provides the basis for determining the best shape and size of a spacecraft and predicting structural requirements. Many methods are used to record and measure the effect of the high-velocity airflow. Tiny instruments inside the model detect patterns of heat and pressure under the various simulated flight conditions. Test data are transmitted to recording and computing equipment through hundreds of instrumentation lines. Some models are coated with a fluorescent oil. High-speed cameras record the oil flow patterns as the model is injected into airflows as high as 6,000 miles an hour. As a spacecraft plunges deeper into the atmosphere, friction continues to slow it down. Simulating this portion of the flight in the wind tunnel causes the model to glow at red-hot temperatures. To examine the flight characteristics as the spacecraft slows down and re-enters the transonic flight regime near the end of its flight, models like this are placed in the large transonic wind tunnel. In this case, to determine flutter characteristics. From launch until landing, most of the critical flight areas can be simulated in the aerospace laboratories of the Arnold Center, obtaining in a few days data which would require months of expensive flight testing. Thus, these facilities help accelerate the development of many high-priority systems. Substantial contributions have been made to programs such as the X-15 rocket research aircraft, the Navy's Polaris, the Army's Sergeant, the Air Force Minuteman, Titan, Atlas intercontinental ballistic missiles, and NASA's Mercury project. The test data provided by the Arnold Center has accelerated by months, even years, the development of many of our aircraft, missiles, and spacecraft. Many other aerospace systems are being supported by tests in the center's 20 major test units and a like number of smaller research units. An active program of research and engineering is directed toward the task of providing advanced test facilities for aerospace systems of the future. Typical is this large vertical rocket cell, which is 250 feet deep. Ultimately, it is planned to test rocket engines having up to 1.5 million pounds of thrust at simulated altitudes of more than 100,000 feet. Construction of these unique testing facilities is under the supervision of the U.S. Army's Corps of Engineers. The operation of the center is the responsibility of Aero Incorporated, an operating contractor for the Air Force. Another advanced unit is this 1,000 feet long ballistic range, which can be described as Cape Canaveral in a tank. This high vacuum cell, part of the Aerospace Environment Facility, is called the Mark I Aerospace Environmental Chamber. Complete full-scale satellite vehicles can be subjected to vibrations, extremely low pressures, temperatures as low as minus 320 degrees Fahrenheit, and the intense heat of solar radiation in simulated flights to altitudes as high as 300 miles. Appropriately, the center is carrying on the tradition of foresightedness that characterized the late General Hap Arnold, for whom the center is named. Aerospace laboratories, creating on Earth much that man must master as he ventures into space. Test chambers that speed the development of future aerospace vehicles. People and equipment that provide for this nation a springboard to space.